Okay, back to finish, continue with this exam, the exam 3 for, the practice of 1 for fall 2021. So this is going to be the third video, and this is the one that we need to look at whether stuff is substitution or elimination in terms of the reaction and how it goes down, the mechanism. So with this one, first thing you want to do is look at what the plus whatever is, because this isn't going to help us. This is called the leaving group. Why it's not going to help us is because for basically all of these reactions, the leaving group is always just a chlorine, a fluorine, a bromine, or an iodine. It's one of those halogens. So one of the biggest things is going to definitely be this, and then sometimes the solvent. That's actually only helpful for Sn2, because if you remember, Sn2 reactions are the ones that have the solvent being the crazy. DMF, DMSO, acetone, which sometimes she draws just like that, it's a ketone, and acetonitrile, CH3CN. If you see one of those, it's definitely Sn2. But otherwise, for Sn1, E1, and E2, you're going to see water, or you're going to see ethanol, right? So the ETOH, or it written like that, and it's like skeletal structure form. So this is only helpful when it's Sn2, because Sn2 has very specific solvents, the DMF, the DMSO, the acetone, and the acetonitrile. So a lot of times, mostly what's going to help is this. Now this plus HF plus HBr plus HCl, sometimes maybe even HI, so a hydrogen plus some halogen, that is definitely, I've seen only with Sn1. So that's what's going to give away that it's Sn1, is because it's plus hydrogen and fluorine, or hydrogen and bromine, or hydrogen and chlorine, or hydrogen and iodine. Now, what do you do next? Great. Well, it's going to help to always think of what this actually is. What is S? Substitution. So something's going to get substituted. It's going to get replaced. It's going to get swapped out. So this, right, the leaving group, it's called the leaving group because it leaves. It always leaves. It's going to leave, but it's going to get swapped out. It's going to get switched out, exchanged for something else. That's what substitution always does. It doesn't matter if it's Sn1 or Sn2. If you can remember that it swaps things out, it switches places, then it can help you organize in your mind, or just like reconnect with where to go or what to do, especially if you feel lost with all of these. You'd be like, okay, I'm going to be swapping something out, right? Because what's the alternative? Elimination. The E1, E2, doesn't matter if it's 1 or 2, those always take things away. They eliminate stuff. So not only is the leaving group going to go and never come back, there's also going to be a hydrogen somewhere else that will also leave, because E1 and E2 both always create a double bond somewhere. So it's going to create that because now the carbons have to share electrons because two things went away. So if you remember that E1 and E2 is elimination, you're going to get rid of stuff and you're going to create a double bond. Because it basically kind of signifies sharing, because other stuff isn't there anymore that they used to share with. So now they have to just share amongst themselves. Substitution, no matter if it's 1 or 2, is always going to swap or just switch places, exchange with something else. And it's always exchanging or swapping places with part of this plus whatever. This plus whatever is the nucleophile. It's the other actor in the situation. It's the one that is either a base, so it can take a hydrogen, or it acts kind of like an acid where it can give a hydrogen. But regardless, just it can keep things oriented in your mind. You're going to switch something out. All right, so what do we do next? What do we do? There's lots of things to do, because there's going to be a few questions you're going to have to look at. I would say it can help once you realize that it's Sn1, is if we have to write the rate law, to just go ahead and write it, because the rate law is always based off of this number. Sn1, the rate law is only considering one thing. Sn2 considers two things. E1, one thing. E2, two things. Sn1, one thing. What is that one thing? It's the substrate. The substrate is the thing, the main molecule, basically the drawing of the main thing that there's a leaving group off of. Right, a chlorine, a fluorine, a bromine, a iodine. Right, so the substrate is this molecule. In both Sn1 and E1, it's the substrate, it's the only thing that affects the rate. So it's the rate law is basically saying what's going to affect how fast this reaction happens. And since it's an Sn1, it's only going to be one thing. Now, they all have the K, because it's a constant. Now, in brackets, what you're going to put in brackets is substrate. So every single reaction, Sn1, E1, Sn2, E2, they all always have the substrate, right? The main molecule in their rate. So what's the main molecule in this one? So the substrate is this molecule with the chlorine as the leaving group and a little isopropyl right there. And because it's Sn1, it's only this one thing, the molecule, that we have to consider. If it were Sn2 or E2, it would be this, and it would be the nucleophile, the plus whatever. Because Sn2 would have to consider two things. Sn1, E1 only has to consider one thing. All right, now you can start with the mechanism, the main part we need to show where all the arrows. So when it comes to this, you definitely want to redraw the substrate, this main molecule. Just redraw it as it is printed, right? And realize, though, that every time this leaving group, because they're always halogens, they always have 7 electrons total around them, and they're bound to a carbon only sharing one of its carbons. So let me zoom in here. This chlorine, it has 2, 4, 6, and the 7th is actually right here. It's already in. That's what this signifies, is that this carbon right here is sharing electrons with that carbon, this chlorine, and a hydrogen we don't see. So there's an electron here for this carbon, there's an electron here from here, because all halogens have 7 outer electrons. That's super important because that is why they all act the same way and why they're doing what they're doing and why we're drawing these. These are the electrons. The seventh, again, is right there that we're not seeing. It's part of 2 in that. Now you want to draw the nucleophile. Here for Sn1, it's a hydrogen bonded to a fluorine, right? And a fluorine is exactly like a chlorine. Chlorine, fluorine, bromine, and iodine, they all have 7 electrons around them. So we have 1, 2, 3, 4, 5, 6, and then the 7th is in this bond. Hydrogen always brings with it 1. That hydrogen's the first element. It's number 1. It's like letter A in the periodic table. It has 1 and it can only handle 2. So that's why it has 1 here, and then fluorine's is right there. So it's using those 2. Fluorine comes with 7, but wants 8. So by hydrogen having its electron, fluorine gets its 8. All the halogens want 8. Almost everything in organic chemistry in those first 2.5, 3 rows in the periodic table, they want 8 electrons around them. That's basically the MO. They're all trying to be like that last column in the periodic table where you have the noble gases that have perfect filled outer shells that everything's basically trying to emulate. So the point is you're drawing these electrons in on purpose because all the arrows that we're going to be using are showing where they are moving to and from. So let me just, fluorine's electrons, 7. Hydrogen's electrons, 1. Chlorine over here, this leaving group, right, has its 7. But there's this carbon here that it's also using 1 from, just like that. That's how chlorine's getting its 8 there. Fluorine's getting its 8 that way. That's super important to realize as on a deep level as possible, because again, that's the whole point of all the arrows and actually what's going on and why things will do what they actually do is because of that. Now, remember, it's S. We're going to substitute. So you always want to redraw the substrate showing the electrons. Redraw the nucleophile showing electrons in Sn1 like this. Now, what you can do is actually begin to show the movement of the electrons. In Sn1, the leaving group does what the name is. It leaves. And that arrow is specifically showing you and telling you that this chlorine pops off and it takes these 2 electrons with it, right? So that it still has its like perfect 8. So this arrow is saying these 2 are going with this chlorine, right? Then what it does is at the same time as it takes those 2 electrons, so see how it actually takes its own, but it actually takes one of carbon's. That's not one of chlorine's original electrons. So it takes it and then at the same time grabs and goes over here and grabs this hydrogen. But it grabs the hydrogen only. It grabs that's why it's called a proton, because hydrogen is 1 proton, 1 electron. If we only grab the positive part, this way you're basically also grabbing only a proton, because hydrogen is just a proton with just 1 electron. So we grab that hydrogen. Now, when you grab that hydrogen, it's not grabbing the electron or the electrons. That's what this next arrow is literally saying. These two electrons stay with this element here, this fluorine. That's exactly what that's all it's saying, is these two stay here because this thing over here came and took the positive part and left the negative. So then they shift and end up right over here. So that's why. So look, we already got the first 3 arrows in Sn1. In Sn1, it only has 4 arrows altogether, so we have almost all of them. The leaving group leaves with 2 electrons, goes and grabs a positive, and doesn't grab the electrons, so we're showing how those stay with this. So what is the result of this? You have to draw that. Basically, the outcome. The outcome of these 3 arrows is what? Well, first of all, what happened to the main molecule, the substrate? This went away. So what did that do? It left an opening, it left an open space, it left the carbon right here with 1 less electron. Its electron was stolen. When that leaving group left, it took those electrons. So this plus, this is the carbocation. It's because it's a carbon that is a positively charged ion, which is what cation means, as positively charged ion. So it's a carbocation. This isn't stable, this isn't happy, this is like a bad situation for carbon, to have had one of its electrons gone. So, but all we're going to think about right now is that's the result of this first arrow having left. Now what is the result of this combining with this? The result of that is that you have the hydrogen and the chlorine, right? So the result of this is an opening because that first arrow shows how it left. This is the result of that because those two combined. And then what's the last thing? There's one more thing. The result of this arrow. The result of this arrow is that you have a fluorine now with an extra electron from the hydrogen that was ripped away from it. So that is fluorine with its, what we already drew, its 6 outer ones you even show, this 7th, and then hydrogens. So really, 2, 4, 6, 8, because it kept these right there. Now because fluorine naturally only has 7, but there's an extra, that's why you draw the negative. It's an anion, and it's a negatively charged, because it has an extra negative thing than it normally does. So the minus is really basically like writing the word electron right there, like there's an extra electron. So now I gotta make this smaller so we can write more. So these first 3 arrows are showing where the electrons are going. And then here we're showing basically the result of what happened. Now we only have 1 arrow left. This is never a good situation, a carbon with a positive. This is okay, but remember also kind of the whole point of everything too is that negatives and positives are always basically attracting each other or shuffling around to neutralize and balance out. So you have a positive right here, you have a negative right there. That is like a perfect storm for the fact that those are going to connect, because when they do, what happens is that they balance each other out. So I'm gonna have this fluorine, bam, goes and connects where the chlorine left and basically reestablishes the same exact dynamic you had here, where you had a halogen connected to this molecule and another halogen connected to this hydrogen. The halogens flipped. They switched places. So, right, we're going to write the result of that placement switch. So it's the molecule again with the fluorine on it now, right? This went there, and that's the result. And we still have that. We don't have to necessarily write that again because we already wrote it here and it didn't end up doing anything else in this reaction. But what you have is this Sn1, but super important. If she shows direction, which here direction is being shown, it's not just a line. It's a wedge, which showing that this thing is coming towards us, it's jetting out towards us. So specifically with Sn1, what you have is what is called more inversion than retention, which means more of the opposite than what you started with. So what's the opposite? We started with a wedge coming towards us, so the opposite would be a dash going away from us. So I would say you're going to have more of this, but you're still going to make this original wedge that we started with. So that's what the product, right, the end result, has more retention, it's opposite, has more inversion. So there's going to be more of this opposite one made with the leaving group going away from us than the leaving group coming towards us, which it is in this situation. The leaving group's coming towards us because that wedge is showing it. So we still get that still happens, it's still produced, but we get more of this than that. And that's what is meant by product has more inversion, more opposite, than it does retention, which is like retaining or keeping the same orientation. So you can do that with the plus to be like, you create both versions. So that's it for the mechanism. Now this question, what type of product distribution would you expect with respect to the 1s blah 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 and 1r? So we see here in the name, she gives us the name of what we started with. We started with an S. So this wedge, in whenever they figured out, you know, the little like the R or the S here, that it was an S. So what's the S? That's S, so then that's S, right? But this would be the opposite, so that would be R. And we get more of this, we get more of the different kind than we do of the same kind. So we get more R because we started with S, so we're going to get more R, even though S is still going to also get made. So what type of would you expect? You expect more R than S. Why? Actually, so because this leaving group, when it leaves, when it pops off and does that, technically, because you know this, I mean, this is all happening almost simultaneously and like barely, not even a second. What happens is this is still basically around. It's somewhere around here. You know, it doesn't like leave and suddenly is like far away. It's still around here, which means when this fluorine comes in to fill this spot to balance itself out, they balance each other out by connecting together, it actually can run into this chlorine that's still in proximity. So that's why you get both versions still, but it causes it to go from the backside. So technically, maybe it's better to show this going like that from the quote-unquote backside, so that you can show, you know, that it's not just like straight on always going forward. It kind of gets forced to go around if it wants to create, well, it wants to be able to fill that without hitting something else in the meantime that it won't connect with, because those two things are negative. They wouldn't balance each other out. So that's why you say the reason you're getting more R than S is because the leaving group, right, causes steric hindrance by still being close or nearby in proximity, still being close by. So it basically causes the nucleophile, which is the HF, the F, the fluorine, to attack from the back. Steric hindrance means, steric means the amount of groups around something. So the steric number would be, for example, how many different substituents or groups or carbon little offshoots are around something. So that still being in proximity nearby as it's left is still causing like a hindrance. It hinders, prevents, it keeps this fluorine from really just kind of like going straight in. Now, this last question is, if the concentration, so the amount, if the amount of hydrofluoric acid, which is HF, was increased, with the rate of the reaction, what would happen to it? Well, the rate law specifically says what players are even involved in affecting the rate or how fast this is going. And since the HF, the hydrofluoric acid, which is the nucleophile / base here, it's not even considered. It doesn't even play a role in the speed, so it would stay the same. It's always the answer that it stays the same if you look at the rate law and you didn't put that thing in the rate law. If it said the substrate, or it said, you know, gave this molecule name and that was increased, then the rate would increase because it's in the rate law. So the same, because not in rate law. Let me make sure it answered everything. Yeah. Hopefully that helps for that one. Okay. Now this one, similar questions. What kind is it? Show the mechanism, answer the questions. All right. Let's look at this. What do we have? Again, this isn't going to help looking at this. This is her drawing out basically ETOH. It's the same thing. ETOH is a solvent in literally all of them except for Sn2. So that doesn't help. This is what you want to look at, the plus whatever. Now, specifically, Sn2 and E2 are the ones that have this combination of a metal and a non-metal. They have this combination of an ion, basically. And I've seen her almost only ever use sodium and potassium, so Na or K, with something. If you have a combination of like this plus something, and this something is Na whatever or K whatever, and this is like just normal generic water or this ethanol, or written as ETOH, then it's definitely E2. It's definitely E2. It would be SN2 if this, the solvent, if you saw DMF, DMSO, or what are the other ones? Acetone or acetonitrile, which she'll write as, what is it? Let me look, it's CH3CN. She writes the acetone sometimes as that, which is the ketone. If this were one of those, DMFO, DMS, that stuff, then it would be SN2. It would be SN2. The dead giveaway with SN2 is there. Because I'm saying that again because SN2 and E2 will often have this combo thing of like a sodium or a potassium with something here. The only thing that would distinguish them is the solvent. If the solvent is just this generic ethanol or water, it's E2. Okay, so now we figured out it's E2. Now what do we want to, yeah, let's write the rate law again, because once you figure out it's what it is, S or E, and it's the 1 or 2, the 1 or 2 part of it is giving away the rate law. Meaning, it's telling you how many things are going to be in the rate law. And there's only either 1 or 2 things. The substrate always is in it, no matter what it is. But for the 2s, the ones that consider 2 things, obviously has the substrate, because they all do, and this plus whatever. So E2, SN2 will also consider and use this thing, the nucleophile. So remember, they always have this K, this constant. So we're going to write, let me copy it here. I'm going to have this substrate, just as she has it written. I'll copy it. Right, that's going to be the substrate portion of it. Then we're going to have the nucleophile in it, because it's a 2. It's an NaOH, sodium hydroxide. All right. So it's easy to just write the rate law once you realize it's the 1 or 2, because 2 things. Those 2 things. We're going to wait for this. Let's draw the mechanism. So the mechanism here for E2 is a little bit simpler in a way, because everything happens at once. It's one step. So E2 is one step with 4 arrows. But, I mean, you can remember that or not. It doesn't matter, because remember, think elimination. What is elimination? 2 things are going to leave. 2 things are going to be gone. 2 things are going to get removed, get eliminated. The first thing is always the leaving group. So what's the leaving group? The leaving group is the thing that leaves. It's the thing that's being shown as connected to the main molecule. So what is it here? It's iodine. Okay, that's definitely going to go away. Now the next thing, because we're not going to add anything, because we're eliminating, we're getting rid of stuff, a hydrogen is the next thing. So the first thing that gets removed is the leaving group. The second thing is always a hydrogen. Hydrogen is what is always removed and taken as the second thing in E1 and E2. It doesn't matter. That's why if you remember it's E, you're eliminating 2 things. The iodine here is the leaving group. It could have been bromine or chlorine, whatever. It doesn't matter. Always a hydrogen. So remember, you want to write and show the electron situation. So iodine, like all the halogens, they all have 7 around them. And again, we only show the 6 because this thing here is showing the 7th that belong and come from the halogen, the iodine here. Then we're going to write out this in its ionic form, in what it actually breaks into, what it really is. So this sodium is Na plus because it has a missing electron. This OH is OH negative because it has an extra electron. Now, it's the negatives you're going to show the electrons around. Oxygen comes with 6. Oxygen comes with, yes, oxygen comes with 6. 2, 4, 6. You don't need to show this, but sometimes she writes it like this, but she's not going to show the fact that right here is going to be 2, 4, 6. This is the extra electron that actually doesn't normally come with oxygen. That's what this is showing. So what we have is we're going to show basically what happens first, what electrons go where first, and what goes and takes the hydrogen. Now, realize that this leaving group is always something negative. There's always going to be something that turns into an anion, right? A negatively charged thing. So it's never going to be attracted to something just like it. So we're going to show how, first of all, those electrons leave with this iodine. Now, when it leaves, it immediately goes and connects with the thing that's opposite to it in charge, the thing that will balance it out, and that basically combines together. And that's always the positive thing. So it's always sodium or potassium, Na or K, right? Now, the tricky part comes is what we know is that it's going to be the OH that is going to take a hydrogen. Because remember, that's the second thing that needs to get taken. So the leaving group's the first thing that's gone, and it goes on its own and reconnects with its opposite, always the positive one of how you break the ion up. The hydrogen is always going to be taken by the negative thing that's left, but you have to figure out and show which hydrogen. A hydrogen from where? Well, what's going to happen is that you're never going to take a hydrogen from something that just left from this exact little spot. Because this is a carbon that already had one of its electrons taken. So it's already unstable. You're not going to be able to take the hydrogen that's off of this as well. It's going to either, right, let's realize what just left. The leaving group's right here, right? It just left. So there's where like this plus is. But we don't draw this in E2. So we know that that's where it just left. So the carbon to its right or the carbon to its left is where the double bond is going to be formed. It's going to be where the hydrogen's taken. It's going to be either taken from here or here, right? It's never going to be randomly taken from somewhere else. The double bond always forms from right where the leaving group left. So it's either going to be right here or it's going to be right here. Normally. So, in this situation, what we have is, what do we have? We have a substituent. This sec-butyl thing right here. What direction is that? That's being shown as going away from us. The leaving group is shown as coming towards us. Right? So let's think this is a carbon and this is a carbon. What's around this carbon? Remember, it needs to have 4 things. 1, 2, 3. It only has 3. So that means there's an implied 4th thing. So we can have 2, 4, 6, 8. What about this one? We got 2, 4, or just 1, 2. Remember, we need 4 connections. That means that there's 2 hydrogens that are secretly here not being shown for the 1, 2, 3, 4. This carbon has its 1, 2, 3, 4. This carbon 1, 2, 3, 4. Right? And the thing that left was right here. So remember that we're either looking at this to connect to make the double bond, or this on either side. They both have hydrogens. Perfect. You're like, oh, this one has more. Okay, that doesn't matter. They both have at least 1 hydrogen. They're both fair game. Which one do you pick? Well, direction is shown, and that's super important, especially for E2. What this means is that if these are in opposite directions, well, let me not jump. That's me jumping, because I have a little shortcut for this. We're standing here and we're looking which one do we need to grab a hydrogen from. Everything's always trying to get as far away from each other as possible, right? So this is going away from us. But this carbon is connected to that hydrogen and these. Well, this is a cyclo thing. They're kind of all locked in. What direction is that hydrogen going in? You have to show that. It's going to always be the opposite of what it's connected to, what that direction is. So this is showing as a dash going away from us. So that means that this hydrogen is coming towards us. It's a wedge, because this is a dash. And this carbon is basically like the core, the mother, like holding all these together. And they all want to spread out, like in an elevator. Everybody tries to, like, maximize space. So whatever direction this is, its hydrogen is the opposite. Right? I hope you're following that. Because the point is, look over here. Again, this is locked. These bonds are locked in because it's a cyclo, so there's no, coming towards us or coming away from us. It has a hydrogen that's going in both directions, right? Because they want to spread out. This was coming towards us, and when you take a hydrogen in this scenario, it has to be a hydrogen that goes in the opposite direction. What direction is this hydrogen going in? It's coming towards us. This leaving group, what direction is it coming? Coming towards us. They're in the same direction, right? So we can't take that, because it has to be in the opposite direction. So we couldn't take this one because it's also a wedge. We can't take this one, it's a wedge. This is what we're basing it on, the leaving group. So the only option is that. That's the only thing we can take. So that's what we show. These electrons come and grab this hydrogen, and only the hydrogen. And what happens when you grab something? When you grab something, you only grab this positive part. It leaves the 2 electrons. So you had hydrogen's electron here, and you had carbon's electron. Well, we only grabbed the hydrogen, so these 2 electrons bounce up over here. That's the last arrow. They stay with the molecule. So now you have to basically draw the result of all of this. What happened from all these arrows? Well, let's go back. this molecule, what happened? This iodine broke off at the same time, combined with this sodium, positive, opposite charged, right? And then this OH, this hydroxide, came in and grabbed a hydrogen, which basically is a positive proton, so also an opposite charge. Grabbed it, didn't stay, but took it with it. So we have two new connections, right? We have the sodium and the iodine together. And then we have this hydrogen and this OH together. But what is HOH? What is two hydrogens and an oxygen, right? It's water. So we're going to write H2O. Not going to write this, even though that's technically what it is, right? So we're going to say plus the NaI plus the H2O, because those are the two new things that formed. But not only that, right? What does this molecule now look like? Well, it's still in its form with the cyclo. It still has that substituent there, right? Now, where did the double bond form? The double bond formed between where, always, the double bond forms between where the leaving group leaves from and where the hydrogen gets grabbed. Because right here and right here, these two carbons now have to share with each other because stuff they were connected to is now gone. This iodine went with sodium, this hydrogen went with this OH and created water. So now these two carbons, bam, are sharing electrons. So that's why they end up like that. They look like that. So the little trick is that you're still going to have to show the direction of where the hydrogen you take is going, and it's always going to have to be the opposite of whatever's shown here. But if the substituent, right, this offshoot part that's like just a normal part of the molecule, if it's in a different direction than the leaving group, then the double bond forms away from it, like here. If this was also in the same direction as the leaving group, right, they're both shown as, say, a wedge, right, or both as a dash, it wouldn't matter, but as long as they were the same, then the double bond would actually form towards the substituent, right, between where what left and what's still there, right? But it didn't. It pulled the hydrogen from right here. So the double bond formed away from it. So that's not the most stable configuration. Most stable would be where the double bonds are where most things are already connected. It's like kind of like putting scaffolding up against like a building with more bricks. It's going to be more stable. So that's what Zaitsev's rule is saying. This question actually asks, what is Zaitsev's rule? Well, what Zaitsev's rule is specifically saying that a double bond is going to form at a carbon already connected to most other things. See, this carbon's only connected to these two carbons. This carbon's connected to that, that, and that. So double bond naturally would want to be there because it's kind of held more strongly. So you could say that Zaitsev's rule is saying that the major product, so like the majority of what's created is more stable, and what's more stable is the double bond at the more substituted double bond, or like at the more substituted carbon. So, did that happen here? The more substituted double bond would have happened right here, but it didn't. So was it followed? No. Not followed. Why was it not followed? Because the double bond didn't connect at most stable point with the substituent. It connected where it had to take a hydrogen from. So yes, that's actually all for this part. Let me make sure we got everything. Yes. So I hope that helped. I know maybe it's a little overkill, but whatever.